Yeah, okay, full screen. All right, so today I'm going to show you a real life application of an optimization that we've recently been working on, and we also and that we had also to use, of course, similar stuff that you use in your course. And we could publish also this paper. We've published that recently in the Journal of Automation in Construction, which is a very good journal. And the title of the work is Multisystem Intervention Optimization for Interdependent Infrastructure. And we call that 3C method. So this is the outline of today's presentation. First, I will talk about the problem and the motivation behind this work. Then the objective of this work. Then the optimization problem. So first, I will show you the concept for solving the problem. So, and we call that 3C concept, and how we modeled our system. So the modeling approach, and finally how we formulated our optimization problem. So the mathematical formulation of the optimization problem. So this is the most important part, of course. I will also show you a numerical example, and finally I will compare this optimization with another work that we are doing, and that's called mitigation controller. That's gonna be a brief comparison just on the main characteristics, the choices that we took in every optimization problem, and the differences. And this is just to demonstrate that there is no one solution that fits everything. So every problem you have to take different decisions. Now let's move to the problem and motivation. As you probably know, in infrastructure asset management, usually we do kind of interventions. Intervention, you can think about it like maintenance of your infrastructure assets, renovation, upgrading, and so anything can be called intervention. So this is just a small example of two different operators that need to implement one intervention. For example, operator A wants to implement intervention every 3 months for their assets, like 3, 6, 9, and 12. And we have another operator, operator B, that they want to execute intervention every 4 months, and that's 4, 8, and 12. And we assume here that both intervention are going to cause interruption to our system. For example, if our system is a road system, and operator A wants to excavate the road to do intervention for a water pipe that's under the road, and operator B wants to just improve the road. So both interventions are going to interrupt the road. So we cannot use the road. So in this case, we have 6 different interruptions for our system. We call them system closure. All right. And what if we could group those activities together? Like we could convince both operators to implement their activities at the same time. In this case, we have A and B here, A and B, A and B, and A and B. So we reduced the system closure from 6 times to only 4 times. And closing the system, in our case, is very costly because it prevents people from using that system. So saving on system closure will yield a lot of benefits. Although operator B here used to do 3 interventions, now they have to do 4 interventions, but the additional cost of intervention is less than the saving of system closure from 6 to 4. So what I will show you in this presentation is how to formalize and implement this idea in kind of optimization terms. So again, the objective is to introduce integrated multi-system optimization approach for infrastructure intervention planning, in which multiple systems can be reflected. It's a lot of words here. So in the next section, I will show you how, so I will explain that a bit better. So in this section, this section is about the optimization. First, I will formalize the 3C concept, so the solution, our idea. And then I will show you how we modeled our problem, and then the optimization problem that we used to solve. So this is exactly, very similar to what I said before, but it's a bit more general. So we have a schedule, so we have time here, we have several intervention activities that are already planned at specific instances in time from A to G. So we want to do this kind of grouping. So the first step of the 3C is to do something called centralization. Centralization means that we set the principal activities as central. For example, there are usually some activities that are central activities, that are fixed activities that have to be implemented at specific moment in time. So they are not really flexible to be scheduled at another instance because they have some constraint. For example, activity A, activity D, and activity G, those are fixed, those are central. We cannot really play with them. All right. Other activities here, B, C, E, and F, are the flexible ones or non-central ones. So we can really change the execution time. For example, we can make B implemented with A or with D and so on. So we have kind of flexibility to play with other activities. All right. So once we set activity as central and non-central, we do this clustering. Clustering means grouping the activities. For example, we cluster A with B, so they are implemented together at this moment in time. C, D, and E together, E with F. So in this case, we reduce system closure from, if you count 7 times, to only 3 times. Okay, but how do we determine the grouping configuration? For example, should B be implemented with A or with D? We should group C with D or with A. We need really optimization for that. For this example, it's quite simple because you can just see it. But in more complex problem, it's really hard to determine the activities that should be grouped together, given all the constraints that we have. So in this case, we need optimization, and this is the third step, calculate. So we find the optimal grouping scheme that optimizes the global benefit in terms of cost and downtime. All right, so actually we need an optimization in order to perform this very last task. Now, I've been saying system and subsystem and intervention activities, but in this slide here, I will show you the connections between all of these elements in our system or in our problem. First, we have the operator. The operator is the manager of one or more infrastructure system. In this case, system 1 and system 2 for operator 1. And infrastructure system can be like a road system or a water plant or power system and so on. So it's independent infrastructure system that can be managed by operator. And every infrastructure system is divided into component or subsystems. So for example, this is water pipe, this is pump, this is road section, and so on. So an item, an entity that can be treated separately, that can be like, for example, maintained separately or yeah. Of course, and finally we have the activities here, which are intervention activities. So intervention activity can be implemented on one or more subsystems. For example, this intervention activity can be replacing a water pipe. This intervention activity can be intervention on the water pipe and on the road section at the same time because they are located in the same location and so on. And of course, we have kind of relationships between the activities and the components or subsystem here, which are these links. So so we model these interaction or these relation using so-called relation matrix. I will show you how it looks like. So we have a metric that models these kind of relationships, but also the subsystems are interconnected between themselves. For example, if you have a road with a water pipe that's underneath, and you want to do a maintenance on the water pipe, then you must also excavate the road. So there's kind of interdependency. If you want to execute intervention on one subsystem, maybe another subsystem will be affected indirectly. So these kind of interdependency is tackled and is modeled using something called interaction matrix. So these two matrices are really key here to capture all these interdependencies. So in our problem, we are going to work with subsystems and intervention activities, not much with systems and operator, but this is just here to give you the full picture. Okay. Yeah. Now to help me better explain those two different matrices, I will just introduce the small example here. This network, this small network that we are also going to use later on in the example. So what we see here is small network for three small infrastructure systems. We have the road in green, the road network in green, and we have the water network in blue, and we have the railway network in brown. These dotted lines here are intervention activities. For example, this dotted line, which is I1, is intervention on this road section, H1. This I2 is an intervention on the water pipe W1, and so on. Now, for the interaction matrix, and the interaction matrix connects, as I said before, subsystems. So it captures the interdependency between subsystems. It's given as follows. So it's square matrix. Yeah, it's called also adjacency matrix, in which you have subsystems in the rows and in the columns. So how we interpret this? I will give you example. For example, if you look at these two subsystems, the H1, the road, and W1, the water pipe, if you want to execute an intervention on W1, you need also to excavate H1, right? In order to have access to the water pipe that's underneath. In this case, we say that W1 affects H1. So we go W1 and we search for H1 and we put number 1. So this means that W1 affects H1. Now the contrary is not true, because if you want to execute intervention on H1, then it's not necessary to stop the functionality of W1, because W1 is just underneath. In this case, H1 does not affect W1, so we put 0. Yeah, and we have, of course, diagonal of 1, because a subsystem affects itself. Yeah, and that's logical, of course. And we do the same thing for every two subsystem to see if there's kind of interdependency between them. And we have this matrix at the end. Now to capture the relation between the intervention activities and the subsystems, we have the relation matrix that connects subsystems with intervention activities. And I will also give you example here to make it clear. For example, this intervention I4, it's for this joint between the 4 roads, so it affects all 4 roads. So I4, sorry, it affects H1, H2, H3, and H4, so we put 1 here, otherwise we put zeros. The good thing about that is that we can capture here the interdependence between subsystem and intervention activities. So we know an intervention activity is going to affect, for example, subsystem H1, and using the previous matrix, we know that H1 will affect will affect itself, but maybe H3 here will affect, for example, R1 as well. So we can capture this cascading system interruption going from one matrix to another matrix. Yeah, now let's move to the mathematical formulation of the optimization problem. Of course, as you know, first we define our objective function. In my case here, my objective is to minimize the cost of the total cost. But what is the total cost? It's composed of 2 different items or functions. The first function is F1, which is the total cost of intervention activities. And that's only the cost related to the intervention activity itself. It means the cost of labor, the cost of material, so every cost that contributes toward executing a specific intervention activity. So it's given as follows. That's the decision variable M, which is whether we will execute an activity or not, multiplied by its cost. For example, if you will execute an intervention activity, so there is 1 inside this matrix, and you multiply it by the cost of the activity. So this is how M looks like. So this is decision variable again. So it's not input, it's something we get out of the optimization problem. So for this example, we have 2 intervention activities, A and B. So we have 2 rows, 1 for A and 1 for B. And whenever we execute activity, we put 1, otherwise we put 0. And same for B, we executed here, here, and here. So 3, 1, otherwise zeros. So our objective is to find the best locations of those ones. So best intervention program. Yeah. So yeah, of course, you multiply this matrix by the cost of every intervention activity, we get the cost of intervention, right? So this is the first part of our objective function. At this stage, we had to make some decision, actually, because our problem, as you saw, is a binary problem. We are only dealing with 0 and 1. So it's a binary problem. We couldn't make it non-binary. As a consequence, we had a restricted number of solvers. So we couldn't use any solver. We were restricted to use the solvers that allow binary problems. And of course, since we are not using binary problems, so it's not continuous, then also we have computational effort. A computational effort, because working with binary problem is more computationally expensive. So this is the first major decision that we took. Now okay, so the other function in our objective function is F2, which is the indirect cost, not the direct, but indirect cost, and that's related to the system interruption. For example, if a subsystem, for example, is interrupted, is not working, then people cannot use it, and then you will have societal impact. Okay, and this cost can be captured using this function here. So again, we have the decision variable, we have the relation matrix that connects, relates the intervention to subsystems, and then the subsystem with the subsystems. For example, if you know that you are going to execute intervention activity, then with the R, you can know which are the subsystems that are going to be interrupted. And with the I, you know which are the subsystems that are going to be affected by the interruption of other subsystems. And of course, you multiply by the cost to get the total cost. And we had here to introduce some a parameter called the Kronecker delta. And the functionality of this parameter here is to avoid overcounting, right? So this is the only thing. It's very important functionality that we needed, but it's the only thing that this Kronecker delta is used for. And the bad thing is that with this Kronecker delta, our problem became nonlinear problem. Because everything is linear, but just with this Kronecker delta, because it's kind of if-else within your function, it became nonlinear. So major decision is that we had to turn our problem into a nonlinear problem, from linear to nonlinear. We tried to linearize the problem a lot, but really we couldn't. We couldn't avoid this Kronecker delta. As a consequence, yeah, of course, we had our problem became more computationally expensive, more computational effort, and of course, the quality of the solution is not. Because with linear problem, you know that solution is an optimal solution. Now we are no longer sure. Maybe we are sure that it's not the optimal one, the global optimal one. Sorry, it's local. And of course, we have some constraint. In our case, we have minimum gap in time between 2 activities with the same type. Like we have A and A, we have minimum gap here. We cannot implement A just directly after previous A. So we have to have minimum gap, and also we have to have a maximum gap. So we cannot wait a lot until we implement this next intervention activity. Now we came into now we have to choose a solver, to solve our problem. So we have some some knowledge, and using that knowledge we need to choose the solver that we are going to use. So our consideration were 3 things actually. First, scalability. Because our goal is not to really solve a specific problem with defined values, but a more kind of a general one, because we want our solution to be applicable to any infrastructure system, to bigger networks. So it's not only for that specific network that I showed you. All right, and that's called scalability. So maybe you're giving me like a bigger network, and you're telling me to solve that network. I should be able to solve that network, regardless how big it is. Thus, the problem can get really big as the system gets more complex. So this is first thing, scalability. Computation effort and time. Of course, time is always important. In our case, we don't really want we want it to be executed in real time, like the example that Maria showed you in a minute. She wanted the result immediately, otherwise the cars would go, and then you have to repeat the calculation and so on. In our case, we have problem, and we have probably, I don't know, maybe a day or maybe less to solve that problem. But of course, we don't want to wait like for weeks or months, but it's not necessary to solve it in real time. Solution equality, as always, we want to trust the solution. Okay, so these are our consideration, and the solution was we chose to go with genetic algorithm with integer variables, right? Because we have integer problems, and this exists in MATLAB actually. Yes. Now for scalability, that's okay, because with genetic algorithm you can accommodate large problems, of course on the cost of solution quality. But how to guarantee a minimum threshold for solution equality? What we did is that we repeated the simulation several times using different initial points. So we kept repeating the optimization one after another, and we collected all the results, and at the end we chose the result, the best result among all simulations. Of course, this added more effort to our computation. It took more time for us to do this job. And for the solution, we adapted the genetic algorithm, the options here. We kind of optimized them for our problem in order to enhance the solution quality, and also to reduce the time of every single simulation. Now, just I will show you a numerical example. That's exactly the same example I showed you before, but now with some numbers here. So, for example, we have the system closure cost. So if W1 is not working, then this is the amount it will cost us because it's not functional for all subsystems. And this is the same matrix I showed you, the interaction matrix between subsystems. We have data on the intervention. We have 7 different intervention activities. We have the gap between 2 intervention activities which are used for the constraint. We have the cost of intervention that is used in the objective function, and we have this matrix as well that relates intervention activities to the subsystems. So this is all the data that we need in order to run our simulation. Well, this is the main first simulation time was only 15 minutes because the network is quite small. Of course, if you increase network, then the simulation time is going to increase, but not exponentially. It will increase in proportionally to the number of intervention activity. This is the main results that we can get out of solution. We call this, what you see here is intervention program. So for every intervention activity, the optimization problems tells us when every activity must be executed. Like activity number 1 should be executed at time step number 3, or maybe month number 3, 8, 11, and 16. Activity number 2 must be executed at 6, 10, and 16, and so on for all activities. And yes, and of course, we have also the cost. So what we see here in red is the cumulative cost, the total cost F1 plus F2, the result of the objective function. And of course, because this is the best known solution for us, so that's the lowest cost we could obtain. All right, and that's of course the summation of the direct cost of intervention activity F1 and the indirect cost that I explained. Yeah, of course, if you look at this, it's not quite really intuitive. I mean, if you just use intuition, you cannot really come up with this kind of configuration. So you need kind of optimization algorithm in order to do this job. Another result I want to show you, if we just focus on the last line, on the last row, if we don't use optimization, it's going to cost us 1,500,000. If we use optimization, it costs 1,200,000, and that equates to around 23% of gain. And this gain is coming just from better rearranging activities, better grouping activities that we use the optimization to do. And that's a lot of gain, actually. If you don't have that algorithm, you're going to use maybe your intuition, some logics, maybe you can get like 5%, but not 23%. Finally, because I'm done with the 3C concept, I just want to draw a little comparison between 3C, what I presented now, and another work that we've already been doing, the mitigation controller. I will not go in detail. So mitigation controller is a tool to optimize the selection of mitigation activities in project scheduling problems with uncertainty. It's not important to understand what we do there, but I just want to show you the characteristic of every optimization problem. 3C concept, as I said, is integer problem. Mitc mitigation controller is also integer problem, 0 and 1. The variables are 0 and or 1. In the 3C method, we use a single simulation, but we repeat that over and over in order to enhance the quality of the solution. So at the end, we have many results, many solutions, and we pick the best one. In the mitigation controller, it has Monte Carlo simulation. So within every simulation, we have a for loop that we do, and at the end, we have only a single solution. Okay? 3C method is nonlinear. Mitigation control is a linear problem, and since it's linear, then the solution that we get is a global optimal solution. Okay, so we don't really need to do this repetition because we know every time we are going to get the same solution, it's linear, and we're lucky to have that linear. Otherwise, it would be kind of really a disaster if it was nonlinear, because would be computationally expensive. And this brings me, of course, this is a reference to the paper that was published here, 3C method. And this brings me to the end of the presentation. Thank you so much. And if you have any question, I'm happy to respond.